So, in the previous part, we talked about the background, therefore a lot of history. In this part, we will sketch the node opening technique. It will be a little bit technical, but I will try to spare most details, but focus on the geometric intuition. So we are gonna construct TPMS using the Weierstrass parameterization, which we record here. For each component of the surface is given by the integrations of a meromorphic one form defined on the Riemann surface sigma here. The three integrands, phi1, phi2, and phi3, must satisfy the conformality condition below. So Q equals the squares, the sum of the squares equals 0. The usual procedure to construct minimal surfaces is to have a rough idea of the topology and the symmetry of the target surface, then encode the information into the meromorphic functions, and finally solve the remaining parameters. One important thing to take care of is the so-called closing the parallels. That is, for any closed curve on the Riemann surface, we want the integration along the curve, which is called the parallels, to vanish. In the case of triply periodic minimal surface, I mean vanish in the flat 3 torus. Let's now recall Karcher's construction of saddle towers. He started from a convex polygon with even number of unit edges. The convexity of the polygon is not necessarily strict, but we do exclude two special cases. First, we don't want the polygon to degenerate into a segment, and we don't want the polygon to appear as a parallelogram with two edges of length 1. Then Jenkins and Serin proved that there is a minimal graph which is unique up to vertical translations over the interior of the polygon, and it takes the boundary values plus or minus infinity in an alternating way on the edges of the polygon. A saddle tower is just the conjugate of a Jenkins-Serin surface. As the Jenkins-Serin graph is bounded by vertical lines, they correspond to curvature lines in the saddle tower that lie in horizontal planes. The unit edge lengths of the polygon guarantee that the curvature lines lie in two horizontal planes at distance 1 apart. Reflection in these planes extend the surface into a single periodic saddle tower. So saddle towers all admit horizontal reflection planes. In fact, there are two horizontal reflection planes modulo the period. And a saddle tower has an even number of Scherkens in correspondence with the edges of the polygon. The Weierstrass data of saddle towers are defined on the punctured Riemann sphere. The punctures correspond to the Scherk ends. The Weierstrass data, that is the meromorphic functions, are given as shown here. Here the capital H is the set of wings. Note that the residue of phi3 here is chosen so that the vertical period of the saddle towers is 2 pi. The pH here denotes the punctures corresponding to the wing edge. The exact positions of the punctures could be determined up to Möbius transforms by the conformality condition, but actually doing this is very difficult. A beauty of the node opening technique is that it is not necessary to know the exact positions of the punctures. Yet we are still able to say a lot of things. So if we perform a kind of Taylor expansion on the vice class data, we will obtain these formula. So if you come down and take a moment to look at it, you will notice that there is a very simple geometric interpretation. The terms under the first brace here, for example, describe half planes. As for the term under the second brace, I claim that it describes a decaying undulation. To see this, note that the vertical coordinate is given by the arc of WHZ, where WH is a local complex coordinate. And the horizontal distance along the wing is parameterized by the logarithm of WHZ. So under the second brace, the first two components contain WH, the term WH here. So this term can be decomposed as a harmonic vibration in the vertical coordinate and an exponential decay in the horizontal distance here. So that's why I say there is a undulation that is decaying. Of course, it's certainly better with pictures. So in the first picture, from a distance, a saddle tower looks like vertical half planes sharing a vertical boundary line. So here we are looking at the saddle tower from above. So the boundary line, vertical boundary line, looks like a vertex, a point here. But if you look closer, you will see that the asymptotic planes of the wings do not actually intersect at a vertical line. So the offset here is seen in the formula as the integration constant mu h. And if you look even closer, then you will see that the wings are not planes, of course, but they undulate in the vertical direction, and the undulation decay exponentially as we travel further away along the way. So we define two quantities based on the expansion. The first one is defined like this, and I don't recommend you to look into the detail of the formula. So it is related to the amplitude of the undulation. And the other is related to the offsets of the wings, of the asymptotic planes of the wings. Now we sketch our gluing process. The components to glue are saddle towers. So we first parameterize each saddle tower to glue on a punctured Riemann sphere. Initially, the saddle towers are all far away from each other. So the conformal model for such a surface is obtained by simply identifying the punctures. And the result is a Riemann surface with nodes. Then we want to shrink the glued wings to bring the saddle towers closer. This is done by a standard node opening technique. So here, delta and t are all small numbers. So around each puncture, we remove a small disk, and for each pair of punctures that were identified, we identify small annuli around them according to this formula. Here, the puncture that is identified to the puncture H is denoted by minus H, actually for a good reason that we will see later. The remaining work is to use the implicit function theorem. The equations to solve include the conformality problem and the period problems that we have mentioned before, and the balance problem, which actually comes from the residue theorem, namely that the residues of the meromorphic function should sum up to 0. I prefer not to get into details of this step as it was very complicated and technical. However, let me explain how the horizontal reflection plane is actually removed. So at some point in our construction, we will make this change of variable. And the new parameters L and phi actually carry geometric meaning. So the meaning of sigma will be clear later. So L can be interpreted as the distance between the saddle towers. And the parameter phi can be roughly understood as the phase differences. Or more intuitively, phi is the difference of the heights of horizontal reflection planes of saddle towers. So in all previous constructions that glue saddle towers, for the sake of convenience, the parameter t was always assumed to be 0. So phi is either 0 or pi, meaning that all saddle towers share the same reflection plane. But we allow phi to take other values, thereby break this symmetry. This is how we remove the horizontal reflection planes.